We are here now to find out the capacitance of a parallel plate capacitor. This type of capacitor has got two plates, large plates having certain area. You can see these are the two plates having minus Q charge here, plus Q charge here, and the distance between them is D. This is the geometrical shape of a parallel plate capacitor. The charges do develop on both the plates. For our derivation and for other parts, we take into consideration that the charge is uniformly distributed and the electrical field within the capacitor is as if the plates are of infinitely large size. You will recall that the electrical field due to infinitely large sheet is sigma upon epsilon naught, which is Q upon A epsilon naught. So you can see here the charge distribution is like this. We have shown the positive and negative charge are distributed on both the plates. Positive plate is having a positive charge, plate number 2 is having a negative charge, and the electrical field is vertically downward. Distance between the plates is D and the area is A. The surface charge density is sigma over here, it's minus sigma because it's a negative charge in this region. You will recall that the electrical field is given by sigma by epsilon naught between the two large sheets oppositely charged. So we place the value as sigma upon epsilon naught, which is Q upon epsilon naught A. We also recall that the electrical field is mathematically equal to potential gradient, or delta V becomes equal to electrical field into distance, and this is the basic concept, basic relation between the electrical field and distance. So we substitute the value of electrical field from the above equation and we get the value of delta V is equal to ED upon QD upon epsilon naught A. The basic equation of a capacitance is Q is equal to CV, which gives C is equal to Q upon V. Using this basic concept of capacitance of a capacitor, we place the value as Q upon delta V becomes equal to C. This is QD upon epsilon naught on the denominator, and numerator has got Q. So we place these values, and on calculation we get the capacitance of the parallel plate capacitor as epsilon naught A upon D. This expression tells us that the capacitance can be increased if area is increased or its distance between the two plates is decreased. Now, increasing the area has got a practical limitation since capacitor has to be used in a circuit, so we cannot have a very large dimension for the area. Second thing is to decrease the distance. When we decrease the distance beyond a certain level, we might have the more electrical field which might leak the charge. So D also has got certain limitations from the point of view of dielectric field strength. So we have to maintain relation between A and D such that neither of these two challenges are there to have a breakdown of the dielectric. So Q upon V is C, and we take this for derivation. C is epsilon naught A upon D.